let's get started. So we are in Chapter 8, Unit 8. You must have gotten my email, hopefully, one of the 2 emails that went out last night. One was from Gradescope, letting you know that the grades for the Gradescope part were up. I then translated those to Acorn, so you can see both now your Gradescope grade and your multiple choice grade and the combined grade, and that is midterm 2. And so I said in the email a lot of things. One of them was that we're going to drop one of the 3 midterms, put that onto the final, if it's to your advantage. So if you get 90, 90, 90 on the 3 midterms and 70 on the exam, I'm not going to do it. But if it's the other way around, absolutely, I'm happy to put more emphasis on the final if that benefits you. I think the way we did the marking scheme this year, the final isn't worth as much as it normally is anyway. So I feel like if you've been doing well all the way along, there's not as many eggs left in that basket, which is a good thing. Overall, as I said in the email, I was very impressed overall with how people had done on the midterm. I think people, mistakes that I used to see commonly on exams, there weren't very many of this year. And, maybe some of that was the open book nature of it. But I think overall people are in a really good place. Usually, I'd say there's a lot more people in a comfortable place at this point in the course than there normally is in most other years. Usually around now, I'd say it's maybe 50-50, where 50% of the class has got a decent handle on it. And by that, I mean probably could get 75 or better on the test. And then usually the other half are struggling to fit together all these pieces. And they may understand the sort of little one-off items that we've done, like carbocation stability, how they're ranked, or these kinds of things, but are having trouble integrating all that information together to do all of the mechanism work that we've been doing so far in the course. If you have all that together and you're doing great, fantastic. That's really good news. If not, if you're really still struggling to put all those things together, there's still time. I see a lot of people between now and the final exam figure it out and put all those pieces together, and really, like, I've seen 20, 30, 40% jumps in people's grades going from midterm 3 to the final exam. And I understand too, part of that is that you guys have a lot going on. It's not just this course that you're in. And I know others, like some people in the class had other midterms the same day or the next morning or this sort of thing. And it's a constant sort of time management issue that you're working on. Whereas I think for the finals, I don't think that's going to be as big of a problem. First of all, you have nothing to worry about except your final exams. You won't have any assignments or labs or this kind of thing hanging over your head. And I don't know what your schedules look like. I don't know if some courses aren't having exams or how that's going to look. But we are late in the exam period. We're in the 19th. So all kinds of time to learn organic chem. I will say this, though. I'd say we're over the hump in terms of course material difficulty. In fact, I'd say Chapter 6 and 7 is the most difficult material in all of organic chemistry, because you have 4 mechanisms that all could potentially compete with each other. They're all a little similar, but a little bit different. And each one of them has these extra sort of factors we got to think about, whether it's rearrangement or E2 orientation or inversion of the stereocenter or all these kinds of things you're dealing with. And for you guys, this is the first time you're thinking about any reaction mechanism, any of these steps. First time you're applying curly arrows beyond acid-base reactions. So these sort of fundamental things that you've already learned or we've already gone over, like what curly arrows mean and how they're used, rearrangements, steps, rate determining steps, all these kinds of elements don't change going forward. Resonance effects, steric effects, you know how SN2 doesn't work on tertiary because the steric effects, all of these different things that we're applying to those 4 mechanisms, those same things always matter. It's the same small, like, I kind of feel like in organic chem, there's like 5 things you got to know. And if you know those, you can feel your way through almost any reaction that we go through. Okay, I see. Could we write the exam earlier? No. The exams are scheduled by the registrar's office, and we have no control over that. Is the final also going to be open book? I haven't discussed that yet, but I liked how it went. So, you guys probably hated the open book, did you?
No.
Open book made life a little easier. So where we're at now, we're in chapter 8, and chapter 8's got a bunch of new reactions. Nothing really new. You know, it's all the same types of stuff we've already gone over in chapter 6 and 7. We're applying it to a new range of reactions. We're going to be able to assemble reactions that we're learning in patterns, like we've seen before, like, you know, stepwise, multi-step reactions. We're going to do some of this. But really the fundamental basic things that we're doing is the same as the last two chapters. And maybe you see what I mean when I said when we started chapter 6, it's like there's a cutoff, like chapter 1 and 5, and then 6 to the rest of the course. It's almost like two separate courses. Or up to the end of chapter 5, it's all kind of like structural things. Then after chapter 5, it's reaction mechanisms, which are using that stuff, but it's a little bit different. So what have we learned so far in chapter 8? We've done 2 reactions. And in fact, the first one is like 3 reactions in one. One, we did hydrogenation. And we said if you have an alkene and you react it with H2, you can make an alkane. Now this doesn't work unless you put a catalyst in. Hydrogen's a gas. We'll not just add on to an alkene unless you put a catalyst. And what kind of catalyst do we use here? Metal, yeah. And there's 4 metals. Can anyone name any of the 4 metals? Yeah, platinum. Yeah, RH. Lead is not one of them. Platinum, palladium, rhodium, and nickel. Anyone, doesn't matter. We also said that if you have a triple bond under the same conditions, you do the same thing. Then we had a variation of triple bond that would give us a cis alkene. And this was using a poisoned catalyst, Lindlar palladium, or sometimes called Lindlar's catalyst. And there was another one. We said if you want the trans, it was the dissolving metal reduction. So we use sodium with ammonia as their solvent. So here we go. We got 4 reactions, I guess, in one. I'm labeling all those as one. And yeah, that's it. All of them have a mechanism that we're not going to get you to draw. So you don't have to worry about drawing a mechanism out for any of these. It involves the metal surface and you have the hydrogens on the surface. Addition, at least for the first 3, we would say the stereochemistry of the addition is syn, meaning if you have an alkene that looks like this, the 2 hydrogens will add on the same face. I'd like to erase that, please. The 2 hydrogens will add on the same side, like that. Next, we did our second reaction, which has a mechanism. I mean, every reaction has a mechanism, but this one we called electrophilic addition. It was ADE2. This was an alkene reacting with HBr or HCl or HI, Proton transfer, step 1, makes the carbocation. And you make this. That's it, whole reaction. Electrophilic addition. It looks very similar to our SN1 reaction of alcohols. Right, SN1 reaction of alcohols with HBr. Yeah, pretty well. I mean, this has an extra step where you have to lose your leaving group. Product is the same. We can make alkyl halides from alcohols or alkenes now that we know this reaction, which is good because we can turn alkyl halides into anything using our reactions in chapter 6. Right? We can eliminate them, we can do addition. We can do neat things like, let's say you have a reaction of this molecule and you want to convert it to this molecule. Okay, how would we do that? Well, you could react that with HBr. Make that. Then you could do an elimination with a small base that'll give you the Zaitsev product. And we can achieve, you know, isomerization is what's going on there. We're doing it in 2 steps. As you can see, we can start to put together our reactions. Okay. We're going to be adding more. So we're going to sort of think of it, these reactions as almost like a toolbox. And every time we learn a new reaction, we're putting it in our toolbox. We can bring it out and combine it with the other ones, make sequences of reactions that allow us to make new products. Okay, so that's where we are. We finished 2, the hydrogenation ones and the addition of HX. We also have, we're going to jump into number 3, which is acid catalyzed hydration. This is starting with an alkene, and we're using a mixture of 50% sulfuric acid, 50% water. So what happens if you mix sulfuric acid with water? Sulfuric acid is a strong acid. It will protonate water to make H3O+. There's obviously a very acidic solution, but we've got water in there. Not like when you have conc sulfuric acid, we know that does dehydration, that makes alkenes. If you use 50-50 sulfuric acid water, it'll turn the alkene into an alcohol. This follows Markovnikov's rule, which you might remember is the rule that the hydrogen goes on the less substituted side of the double bond. The other part, the X, the OH in this case, goes on the more substituted side. And that's the basis of this is that it goes to the more stable carbocation. Okay? So it turns out this has the exact same mechanism as addition of HBr. It's still ADE2. It basically looks the same as before. So it looks like this. Step 1, proton transfer. And you can use sulfuric acid as the acid. I'm using H3O+ as the acid because sulfuric acid and water, you have a lot of H3O+ present. Just use the strong acid, one or the other. Proton transfer to the alkene, and the hydrogen will add to the less substituted side of that alkene because it wants to make the more stable carbocation. In this case, the carbocation we're making is secondary, which in a normal situation, you would look out for possible rearrangements here. Now, in this case, it doesn't rearrange. I did start the recording here. Yeah, good. You would look out for rearrangements, which can't happen in this example. Then water is around. Water is a nucleophile and a base and an acid. Water's everything to everyone, right? Whatever you need, water will do it. So it's acting as a nucleophile here, and it comes in and attacks the carbocation to make an oxonium ion, and then the oxonium ion can lose H+. Now what's interesting here is if you look at this mechanism, it's the exact reverse of acid-catalyzed dehydration. Think about it. First step in acid-catalyzed dehydration is protonating the alcohol to an oxonium ion. Next step is loss of oxonium ion to make a carbocation, and then elimination of a beta hydride or hydrogen to make an alkene. So all the steps of this mechanism are the exact reverse of the dehydration. So why would it go on this side or this side? Why would it go forwards or why would it go backwards? Conditions are the same too, almost. We either use conc sulfuric acid to do dehydration and drive it to the left, or we use 50-50 sulfuric acid and water, and that drives it to the right. So this is a mechanism that we say is reversible. It's not really a new mechanism, if you want to think of it that way. It's electrophilic addition. Yeah, we give it a new name, ADE2, but it's really just E1 backwards. And you can make this reaction run backwards by adding water to the sulfuric acid mixture. Yeah, so that's what we just said. So basically, this is the overall reaction mechanism. We have an alkene, we're reacting it with water, acid is a catalyst, acid catalyzed, and you make your product. So basically, the way this works is like an equilibrium between the alkene and the alcohol. Water is a reactant, so if you add a bunch of water, it's going to push this equilibrium to the right, and you get acid catalyzed hydration, and you get alcohol mostly as a product. If you use concentrated sulfuric acid that doesn't have a lot of water, it instead drives this to the left, you get dehydration, and you get an alkene. This is a neat example of a mechanism that can go both ways. And in fact, in principle, every single mechanism can go reversible in either direction. There's a principle in organic chemistry called the principle of microscopic reversibility, which means that if a reaction follows a certain mechanism to give you a product, the reverse reaction is going to go through the exact same mechanism through the exact same steps in reverse. It's not going to use a different mechanism. And the reason is it's going to pick the lowest energy pathway to go forward. It's also going to pick the lowest energy pathway to go backwards. It's not going to go find some new, because if it's a better way to go backwards, it's also a better way to go forwards. So yeah, this is the same, but otherwise this is the same reaction as before. The conditions are important though, whether it's pure sulfuric acid or 50-50 sulfuric acid water, you'll get a different product, a different outcome. There's a lot more attention placed in Chapter 8 reactions to the conditions that we're using for each of these reactions. Relative rates here, what you see is the fastest rate, by a factor of 10 to the 11, which is a big factor, for making alcohols that go through tertiary carbocations. Secondary, not as good. Primary, really slow. And when we say that you can't make primary carbocations, we actually don't have a different mechanism in this example for a primary example like this. They're super slow, not good reactions. In fact, this is the only molecule, ethene, that can do this reaction, because every other alkene is going to be at least secondary. And so yeah, we're only going to kind of deal with ones that are non-ethene in terms of mechanism. There is a different mechanism for the other one. It does not go through a primary carbocation. But we're not going to deal with it. So it makes sense if you can make a more stable carbocation, the reaction's faster. That suggests the rate determining step of that mechanism is, guess what? Formation of the carbocation. Every time there's a carbocation, forming the carbocation is going to be the rate determining step. Proton transfers are fast. Nucleophiles attacking a carbocation are fast. Losing leaving groups is fast. No, not if you're making carbocations. Rearrangements, carbocations, rearrangements. Nothing new. You've learned about rearrangements before. This is a carbocation mechanism. So there's rearrangements here again. So if you make a carbocation like this, we would look for a possible rearrangement because this is a secondary carbocation, and there is a possible, you probably have seen this cation before, this exact one, and this can do an alkyl shift or a methyl shift from the left carbon, which looks like that, gives you a more stable tertiary carbocation. Then the water can add to give you this tertiary alcohol. And when I put these sort of like double arrows like that, it just means there's some more steps to the mechanism that I'm skipping. We're going to fast forward. Actually, that's kind of like, if you like, the fast forward button kind of looks like that, doesn't it? So we're fast forwarding through the rest of this mechanism, going right to the product. Awesome. So we got sort of 6 reactions, sort of 3. All the hydrogenation ones, which was 4. Addition of HX, and addition of water. Now, I don't really like calling those 2 separate reactions because they have the identical mechanism. Okay. Not, I guess, identical. One difference is when you add water, because it's a neutral nucleophile, there's an additional step where you got to remove H+. You don't have to do that with bromide because it's negatively charged. But besides that difference, same mechanism, same rate determining step, same carbocation, same Markovnikov rule, all these sorts of things. Both have rearrangements. So we're going to jump to the next reaction, which is called Oxymercuration-Demercuration. Again, a very nice name, very descriptive name. It's telling you what's happening in the reaction. We're going to oxymercurate it. We're going to add oxygen and mercury. And then we're going to demercurate it. We're going to take the mercury back off. Okay. So I have the mechanism. We're not going to worry about the mechanism for this reaction at all. But what happens is if you have an alkene like this, we're going to treat it with water and mercury acetate, mercury 2 acetate. In the presence of THF, what happens is you add OH to one side and then a mercury acetate group to the other side. That's step 1. This is a 2-step reaction. And then what you do is you throw in NaBH4. NaBH4 is called sodium borohydride. It's a hydride source. It adds H-. It's a reducing agent. And what it does is it kicks out the mercury group and replaces it with a hydrogen. So this is a hydration reaction. It's a 2-step reaction that adds OH to one side and hydrogen to the other. And you look at that and you say, who would want to do that reaction? First of all, it's 2 steps. Acid catalyzed hydration is just 1 step. This is a 2-step reaction. So 2 days in the lab instead of 1. Also, you got to use a mercury salt. And what do you know about mercury? Yeah, it's bad for you. It's toxic. And as a chemist, I'm not worried about its toxicity so much because we have ways of protecting ourselves. We have gloves and we have fume hoods and the whole thing. What I'm worried about is paying to dispose of the waste. And for every mole of product you have, you get a mole of mercury waste. And mercury is heavy. So, if you're making 10 grams, you might get 100 grams of mercury in the end. And that's just waste. And maybe in the lab, that's doable. But imagine you're in industry and you want to make 7 tons of aspirin or something. And okay, we're going to make 70 tons of mercury waste. And then your manager says, no, find a better way. So why the heck am I teaching you this reaction? And why would you want to do this reaction? This is what it looks like. Okay, we have an alkene here. It adds OH to one side, hydrogen to the other. It does hydration. It does Markovnikov hydration. But look at this reaction. What would this one give you if you did addition using sulfuric acid and water? If you did acid catalyzed hydration, think about what would happen. You would make this carbocation. What would that carbocation do? It would rearrange. to this. This is a different product. So the advantage of oxymercuration-demercuration is that there's no carbocation in the mechanism, and therefore there's no rearrangements. So if a rearrangement happens with acid-catalyzed dehydration, and that's undesirable, you can use this reaction instead. Still Markovnikov, but it'll happen with no rearrangements. So now we have kind of two ways we can do hydration. I'm not gonna ask you to draw the mechanism for this one. So I say here the addition is neither anti or syn. Remember, syn means they go on the same. Anti means they go on opposite faces of the alkene. This one you get a mix. Just like the previous example with carbocations, you have 50-50, which face of the carbocation the nucleophile adds to. You can make either one. But there's no rearrangements, so this is the advantage of this particular reaction. Now, it turns out we're going to teach you a trio of reactions. So let's say, for example, we have this alkene, one decene or decene. I think it's decene is maybe how you say that. 10 carbons, a double bond at the end. If you do oxymercuration-demercuration or treat it with 50% sulfuric acid, by the way, if you see 50% sulfuric acid, realize the other 50% is water. You're going to make this. You're going to make 2-decenol or decanol. Right? It's going to go on carbon 2. Let's say you want it on carbon 1. Can't use acid-catalyzed hydration because that's Markovnikov. You can't use oxymercuration-demercuration. That's also Markovnikov. It's just like Markovnikov with no rearrangements. What if you wanted to add it the other way around? What if you wanted your OH over here? Do we have a way of doing that? Yes, we do. Another new reaction. So hydration, turning an alkene into an alcohol, we have 3 variations we're going to look at. Acid-catalyzed hydration, oxymercuration-demercuration, hydroboration, oxidation. Complicated sounding names, but they're actually very informative. Hydroboration, you're going to add hydrogen to one side, boron to another, and then we're going to oxidize it. So it's another 2-step reaction. And when I say 2-step reaction, I don't mean 2-step mechanism. I mean 2-step reaction, meaning you got to add a bunch of stuff in the flask, stir it for a while, and then fish your product out, and then add a second dose of stuff. So it's like 2 separate steps in the lab, 2 reactions you got to do. So yeah, that does the hydroboration oxidation. So we're going to look at the conditions for this reaction, how it's different, and what advantages this reaction might have for us. The mechanism actually is pretty simple. I'm not going to get you to draw this one out, but you need some source of BH3, which we call borane. And borane, you can buy it. Comes in 2 different types. You can get B2H6, which is a dimerized version in a solvent called diglyme. And diglyme is an ether solvent, so it's fairly nonpolar, but it's got some OHs that can stabilize it. Or you can have BH3THF. THF is another ether solvent we haven't seen yet. So THF has this structure. Okay, it's a cyclic 5-atom ring where one of the atoms is oxygen. It can act as a hydrogen bond acceptor, but not a donor. It's not a product solvent. It's not very polar either, so we don't call it a polar product solvent. This would be called like a non-polar. It's slightly polar, okay, but it's not strongly polar. You couldn't dissolve salts with this. What happens is if you have BH3 as well, is these can combine. No. These can combine give you this. We would call this like a Lewis acid base adduct, maybe, or complex. So it's a source of BH3. B2H6 actually is those inorganic people here might have seen B2H6 before. It's a very, very weird structure. Have you seen B2H6 in inorganic? No? It's weird because that's the structure. What's weird about that structure? Yeah. Hydrogen's making 2 bonds. And, you know, this is how it exists. People have thought maybe it's like there's some kind of like a hydrogen bonding thing going on, but that's not true actually. Those BH bonds are the same on both sides. So it's like, it's not that, it's this. It's called a 3-center 2-electron bond, where there's like 2 electrons in that bond, but it's spread over 3 atoms. It's kind of weird. We're not going to get into it. Okay, inorganic, yeah, that's the place for this kind of stuff. But those are the 2 sets of conditions that you will see that are hydroboration oxidation. B26, diglyme, BH3, THF, tetrahydrofuran is the name of that. Either way, these are a source of BH3. BH3, boron does not have a full octet here. 6 valence electrons. And what it can do is it can add to a double bond like you see in this step. The boron likes to go on the less substituted side, the hydrogen on the more substituted side. So that's anti-Markovnikov. It goes the other way around. It puts the boron on the less substituted side, hydrogen on the more. The oxidation step uses hydrogen peroxide, H2O2, under basic conditions, NaOH, or OH minus, KOH, LiOH, your favorite strong base. So 2 steps. Overall, what this achieves is hydration of the double bond, anti-Markovnikov. So that's when you would want to use this one, when you want to put the OH on the less substituted side. We use one of the other 2 if you want on the more substituted side. Acid-catalyzed hydration is better because it's easiest, but it's going to rearrange and you don't want it to rearrange. You'd use Oxymercuration-Demercuration. The addition for the hydroboration oxidation is syn, because what happens when the borane comes down, the BH3 comes down, the transition state kind of looks like this, and the boron, the BH2, and the hydrogen both add onto the same face of the alkene. It's syn. It's just like hydrogenation was. They both add onto the same face, like you see here. And then when you do the oxidation, when you turn the boron into the oxygen, it doesn't change anything. It just puts the oxygen where the boron was. So if you have an alkene like this, this is the alcohol you're going to get. Notice the hydrogen that was added and the OH that was added are syn. So it gives you the trans product here. Cool. The other 2 hydration ones weren't syn and they weren't anti. They were like a mix. If there was a stereocenter being formed, you get a mix of them. All right, we're flying through these reactions. 3 hydration reactions, right? Carbocation 1 that does rearrangements and Markovnikov. The non-carbocation 1, that's also Markovnikov, and then hydroboration oxidation, which is anti-Markovnikov and syn, and no rearrangements either. Great. Addition of halogens. So this is going to be your second mechanism and final mechanism in this chapter. Addition of X2. X2 being something like Br2, Cl2, actually that's it. Not F2 and not I2 either. Reaction is done often in alkane solvent like hexane. Maybe it's something nonpolar. It could be something like CH2Cl2 as well, which is dichloromethane. It's another solvent that's good to use in the lab. It's cheap, evaporates easily, non-toxic, doesn't destroy the ozone layer. All these things that we like about solvents. And so what these do is make a dihalide like this. Bromine adds to one side, the other bromine adds to the other. These make a molecule that we would call a vicinal dihalide. What does vicinal mean? It means if you have a carbon. There we go. I got an answer online. What was it? What was the answer?
Oh, they're attached to adjacent carbons.
Very good. So if you have X1 and X2, we would say those two X's are vicinal on adjacent carbons. What if you have this? What do we call that? When they're both on the same carbon. Geminal, good. Lots of great words in chemistry. Another thing is that great terminology in chemistry that's good to know. A CH3 at the end of a chain. What do we call a CH3 group? Methyl, yeah. What do we call a CH2? You may not know this one. This one's called a methylene. And if you have a CH, that's called a methyne. If you have one that's all carbons, quaternary. Or if you have one that's like say on a ring, like a benzene ring, there's also no hydrogens, but it's sp2. That one's called ipso. Lots of great names for all these. Anyway, that's not related to what we're doing, except that it's all organic chemistry. Okay, so we have our alkene. Bromine adds, doesn't rearrange, adds bromine, one to each side. This, by the way, is used industrially to make fats. Remember how we talked about fats, how you can hydrogenate them to turn them from saturated to unsaturated? There's another reaction where you can brominate fats, and it adds all these bromines onto the chains where there was once double bonds. And these are called brominated vegetable oils, and these are used in the food industry, and they're often added to citrus drinks, things like pop or juice. And the problem with citrus drinks is some of the flavor compounds are nonpolar and don't dissolve in water, and then they float to the surface, and then you get this like layer of like like orange peel kind of flavor or lemon citrus kind of flavor sitting on the surface. And you don't want to shake it up if it's pop, right? And so what they want to do is disperse that throughout the drink, and they add brominated vegetable oils, because what brominated vegetable oils have with all these bromines is density. Bromines makes the chains heavy, makes it dense. So if you mix it with the oils that you'd find in the juice naturally, you can adjust the amounts so that the mixture of the oils and the brominated fats have the exact same density as water, and therefore won't float to the top anymore. They'll stay dispersed in the water. So you can find brominated vegetable oils in pop. This was a change.org petition for Pepsi to remove brominated vegetable oils from all drinks, because some people believe that this has negative health effects if you drink this stuff. I'm not an expert on this aspect of human nutrition. My feeling is if you're really concerned about your health, Mountain Dew probably isn't your first choice anyway. But yeah, I think all pop has negative aspects. I agree. So yeah, you're not going to turn Mountain Dew into a health drink by removing brominated vegetable oils. This was the name to Pepsi Cola. You saw fit to remove brominated vegetable oil from Gatorade, but left this potentially harmful substance in Mountain Dew, a substance which belongs to the family of chemicals used to make items flame retardant, does not belong in beverages. So this is a terrible reason. You know what else is a flame retardant? Water. Right? The fact that this compound is not even a flame retardant, but is related to some flame retardants, doesn't mean that it's not safe to drink. I'm not saying it is, right? But that's not the argument you use, right? So they're saying, please remove. I did not sign this, by the way. Yeah. By the way, there's tons of this kind of stuff online. If anyone has taken my Chem in Our World course, we talk about this a lot. Stereochemistry, one thing that's interesting about this bromination reaction, everything's interesting about this reaction, but particularly interesting about this reaction, is that the addition occurs with anti-stereochemistry. So if you have an alkene that's flat, and like on a ring like this, so there's not free rotation, the two bromines will add to opposite faces, which is kind of weird. Like if they added Br2 comes down, bang, you have your compound. You can kind of imagine that maybe, kind of like hydrogenation. But no, this one always goes on top and one always goes on bottom. So we have to account for this. We have to we have to explain why this is the case mechanistically. You can use bromine, you can use chlorine. Iodine is not reactive enough. Generally speaking, iodine will not do this reaction because it's too sluggish. Fluorine will make the whole container explode. It's too reactive. It won't stop at reacting with the double bond. It'll react with the rest of the molecule too. Fluorine is a beast, F2. So we don't use fluorine for this reaction either. Yeah, there's a saying, how can you tell you've met a fluorine chemist? And you shake their hand and see if they have all their fingers. Because if you're a fluorine chemist, you don't. Here we go. So it's anti. Why is it anti? Relative rates, super slow. It gets faster the more substituted the alkene gets. Tetra being the best. Tetra is the best. So this might look at it and you might say like, wow, we're making a carbocation. Because carbocations get faster the more substituted, like they get more stable the more substituted. So if your rate determining step is forming a carbocation, yeah, increasing the substitution should increase the rate. Although it doesn't explain why you'd get a big jump going from that one to that one. Because let's say you had a Markovnikov carbocation that ended up here versus here. Both of those are tertiary. So why would one be, I don't know, I'm not going to do math on the fly here, but like 1,000 times faster? No, I will do math on the fly. 200 times, 500 times faster? Ish? No, 200 times faster. Yeah. 200 times faster. If that was just it was just a regular carbocation mechanism, that wouldn't make sense. Also, remember carbocation mechanisms, when you add things, it's like 50-50 which face you go. This is not 50-50. It's always on the backside. So this is not going to be just a simple, straightforward carbocation mechanism. It's a little different. But related. Everything's related. So here's what happens. Bromine, Br2, or chlorine, they're nonpolar molecules. They're diatomics. And you can think about this molecule as being kind of like peanut-shaped, where the peanut, outside of that is the electron cloud. And it's evenly distributed on this molecule, right? Like if you have dispersion forces, you can shift electron clouds. What happens when you bring it down close to an alkene? The alkene has a lot of, it's got a pi bond above and below with electrons. That repels the electrons in Br2. So what you get is something that looks more like this, a little exaggerated, but the electrons sort of flee to the other side of the bromine because it wants to get away from the electrons that are in that bond. So it becomes polarized. That Br2 becomes polarized with the positive bromine coming close to the alkene. So a polarized Br2, like sigma plus, sigma minus, it's kind of like HBr or HCl, sigma plus, sigma minus. And we know what HCl will do. It'll add H plus. Well, this is going to do the same thing. It's going to add Br plus. So this is what happens. And this is the most complex step you will see because there's 3 arrows. Maybe E2 is more complex. E2 has 3 arrows as well. But what happens is you can see there's an arrow, the first one. I'm going to label these 1, 2, and 3. Arrow 1 means the pair of electrons in the pi bond, the carbon-carbon double bond, attack the bromine to make a carbon-bromine bond. Arrow 2 means the BR-BR bond breaks. The pair of electrons in that bond goes to the bromine at the top to make bromide, Br minus. The third one means a lone pair from that bromine attacks that carbon to make a bromine carbon bond. So all this happens at once. And what this does is it gives you this 3-membered ring, 2 carbons and a bromine. The addition of that bromine is syn, right? Like the 2 bonds coming to the bromine are coming from the same face of the alkene, because you can't make an anti-3 atom ring. You get bromide. That bromide was the top bromine from the left. So this step, it's only complex because a lot happens here. All in one step, all in one transition state. You break the Br bond, it loses, and you make 2 bonds from that bromine to those 2 carbon atoms. So it kind of just goes on, bromine, and the bromide flies away. And you make this thing. This is called a bromonium ion. If we use Cl2, it's called a chloronium ion. I think in general you call them halonium ions. They're halogens. That's not a carbocation. It's a little like one though, because it's positively charged. But at least in this example, every atom has a full octet. You have a positive formal charge on an atom that's kind of electronegative, bromine, or chlorine's even worse. That's okay. We've seen positive charges on oxygen before, oxonium ions. Oxygen is more electronegative than either of those. We have a 3-membered ring, which maybe isn't ideal because we have lots of angle strain, we know, in 3-membered rings. But no matter how you slice it, this is going to be kind of hot. This is going to be wanting to react. It's not very stable because of the angle strain, because of the positive charge on an electronegative atom. You know, it's better than a carbocation, but not a lot better than a carbocation. So the rate determining step for this reaction is formation of that bromonium ion, that high energy intermediate. Now we're not done. We have to add the second. The second Br minus has got to come back and do something here. And I don't want to talk about that right now. What happens is it comes in, attacks the bromonium ion from behind. What does this reaction look like? Yeah, it looks kind of like SN2, doesn't it? In fact, it is an SN2. Except because the bromine is attached twice, it doesn't leave, it just breaks that one bond. So the second bromide comes in, attacks this carbon from behind, so in the product it's attached from behind, and the Br that's in front, that's still hanging on there, it's in the front there. SN2 is always backside attack. So because it's backside attack, it always has to attack the opposite side from where the bromonium ion bromine is facing. So it's always anti for that reason. Always an anti-addition. Gives you trans products. Okay, that's SN2. By the way, this is what I was talking about, the stability of that bromonium cation. You can think of it as being like a carbocation with a bromine attached, where the bromine kind of leans over and puts its electron pair down to make the bromonium. It's more stable than a carbocation. So it forms this ion and not carbocations. So because this is not a carbocation, it doesn't rearrange, which is good. Nice SN2, nice two-step reaction. So here's another image of the same reaction. We have an alkene, which is flat, because those carbons are sp2 hybridized, trigonal planar. Br2 comes down. Those are the arrows as we would draw them. Lots of arrows going on here. Br bond breaks. You make the bromonium cation. The Br minus has to migrate to the bottom side, or maybe it's a Br minus from a different step, from a different molecule undergoing the same reaction. And then it can attack one side or the other to make your trans bromine. By the way, you could attack either of those two carbons, in which case you're going to get both enantiomers. This is chiral. S, and this one is S as well. So you can cut this or RR. Great, we're out of time. We're doing well. We're marching through all our mechanisms. We've got a bunch done already. We're going to come back. We're going to revisit this particular one on Monday. But yeah, so far so good. All right, goodbye everyone. Goodbye online folks. I hope everyone has a great weekend. And I hope COVID continues to slow down so we can all have Christmas.